Wireless communication systems have to be capable of performing virtual worldwide coverage as well as processing data with maximum rates. Since the terrestrial networks are not capable of covering the entire globe, there are remote regions on board ships, aircrafts, etc. cannot access to high data rate services. To overcome the aforementioned constraints, satellite communications are capable of increasing the capacity of wireless communications with the global coverage. The most crucial component in any satellite communications and radar systems consists of the antenna, whose performance is strongly dependent on the type of antenna configurations and beamforming techniques. Hence, in the research project of performance evaluation of implementing LCVM beamformer for cylindrical antenna array in a smart array antenna applications, we have evaluated the performance of the cylindrical antenna array with performing the LCMV beamforming technique in transmitting data in the satellite communications. Our contributions in this work have been outlined in this slide. Array signal processing refers to the spatial signal processing, which is composed of designing an appropriate configuration of the antenna array for steering the main beam of the radiation pattern in an arbitrary direction of the space and performing beamforming techniques for placing nulls of the radiation pattern towards interference signals and steering or producing main beam of the radiation pattern towards targets based on the measured weight vectors. In the framework of array signal processing, in this slide, we have presented a brief comparison among different antenna arrays. A uniform rectangular antenna array includes two main disadvantages of a weak performance with a low resolution and having an additional major lobe on the opposite side of its main lobe with the same intensity. A main disadvantage of a circular antenna array consists of having grating lobes and side lobes. Furthermore, since the radiation pattern of the circular antenna array does not include any null in the azimuth plane, therefore it has a weak null steering performance. However, a 3D configuration of the cylindrical antenna array has a better performance in the elevation angle, and its radiation pattern includes several nulls in the azimuth plane. Multi-layer elements of the cylindrical antenna array show the better performance in terms of scanning angle and thereby spatial resolution compared to the planar antenna arrays. Beamforming techniques can be deployed using any type of optimization methods or two well-known approaches of minimum variance distortionless response or MVDR and linearly constrained minimum variance or LCMV, or a combination of the aforementioned approaches. Although the MVDR beamforming technique is capable of determining optimal weight vectors for the beam steering direction, the non-steering performance of this technique remains unsatisfactory. To overcome the aforementioned limitation, we have implemented the LCMV beamforming technique for the proposed cylindrical antenna array. The LCMV beamforming technique can reduce interference signals without losing information strengths. Compared to the MVDR beamforming technique, the LCMV beamforming technique includes several different merits of better performance in suppressing interference signals, a drastic reduction in side lobe level values, a significant increase in signal to interference noise ratio values. The proposed cylindrical antenna array with performing LCMV beamforming technique has been demonstrated in Figure 1, which works at the operating frequency of 300 MHz. Each array element is supposed to be a dipole antenna. Its 3D radiation pattern in the right-hand side includes various nulls in azimuth and elevation directions. The performance of the proposed cylindrical antenna array in Figure 1 with performing the LCMV beamforming technique includes several different advantages of a SIR of 2.257 dB and antenna efficiency of 90% and a side lobe level of -25 dB. The adaptive is typically performed over the long-term channel state information as we have demonstrated in figures 3 and 4, frames being exchanged between receiver devices and a wireless access point in a wireless digital communication channel. The antenna array should be capable of providing the required and qualified amounts of signaling for transmitting data through both uplink and downlink passes. In this work, we aim at estimating the performance and effectiveness of the proposed cylindrical antenna array performing based on the LCMV beamforming technique. Hence, it is assumed that we have employed the same configuration of the 802.11 packet format of Figure 5 for transmitting the obtained radiation patterns in the three scenarios in the next slide. In this slide, the effectiveness and performance of the proposed cylindrical antenna array with performing the LCMV beamforming technique in transmitting data in a digital wireless communication channel have been verified compared to the linear antenna array without performing any beamforming technique and the linear antenna array with performing the LCMV beamforming technique. Part A compared to Part B shows a drastic improvement in the performance of transmitting data by performing the beamforming technique. Part B compared to Part C demonstrates a significant enhancement in the performance of transmitting data with the cylindrical antenna array. Consequently, we have verified that both the configuration of the antenna array and beamforming technique can strongly enhance the antenna performance in transmitting data in a digital wireless communication channel. Thank you for your attention.